Okay guys, we're going to be looking at Kruskals algorithm, and like prims, this is an algorithm for finding a minimum spanning tree in a given graph. So prims was kind of like Dijkstra's, and we kind of looked at the vertices and saw where they can go from one another. In Kruskals, you bear with me with the pronunciation of that, you look at the edges. So here's what we're going to do. We're going to start by looking at our edges, and we're going to go in ascending order from our least expensive edges up to the most expensive edges, and you'll see what that means in a minute. So what I'm going to do is I'm going to circle this edge. Let's start with this edge. This is from V1 to V4. And the thing is with Kruskals is you want to look at all of these different vertexes. You'll see I've drawn the different vertices here disconnected from one another. You want to look at them as different sets. And these different sets you want to combine together. So if you were to try to join two vertexes and they were already part of the same set, then you would not be able to join them. So let's start with the vertex, or excuse me, the edge I had circled here, V1 to V4. So we're going to draw that on our little table. So we're going to say V1 to V4. The weight of that's going to be 1, and the action is, well, we'll accept it. Because now V1 and V4 are part of the same set, and we have 1, 2, 3, 4 other sets. See how this works? You can think of it as groups if that makes you feel more comfortable. Next, let's look at the edge from V6 to V7. Also has a cost of 1, so we'll draw it here. V6 to V7 to weight 1, and we want to make sure we go in ascending order because that's going to ensure that we find the minimum spanning tree. So V6 and V7 right now are separate sets. We'll connect them. We can see that we've gone, we have no more 1s left, so now we're going to look at the 2s. Let's look at V1 to V2. Are V1 and V2 in different sets? Currently, yes, they are. We'll connect them, add them to our table. V1, V2, have a weight of 2. We'll accept. I forgot to write accept here. Okay. Next biggest weighted edge is V3 to V4. We'll circle that. Are V3 and V4 separate sets right now? Yes, they are. So we connect them. Mark them on here. V4. Weight of 2. Accept. Let's look at the next one. Looks like we're out of 2s, so we're going to find a 3, which is V2 to V4. Or V4 to V2, whichever way you want to write it, doesn't matter. 4 to V2, and when we look at our drawing here, and we can see, I'm going to put it in a highlighter so you can see, if we were to connect V4 to V2, we would have a cycle. Because V2 and V4 are currently part of the same group. They're part of the same set. They're all connected to one another. So we can't actually join them yet again. So we're going to reject that particular grouping. So we'll just mark it so we can see it. V4, I already drew it. So the cost of that would be 3, but we're going to reject. Okay, we're going to continue as planned. We have no more 3s left. We're going to find a 4. Let's do V3, V1. Weight of that is 4. And is V3 and V1 part of the same? Yes, they are. We cannot connect them, so we're going to reject. Find the next value, which is here, V4, V7. And if you see, V4 and V7 can connect, so we're going to accept this. V4, V7. And its cost is 4. Accept. And then finally, we know we need to connect V5, so we're going to look at V5 on our graph here. And we can see we could either connect it to We'll try them in ascending order. So can we connect V5 to V7? Yes, we can. That is the smallest edge going into V5, therefore we know that has to be the one we use, and we are done. And we'll, for completeness sake, we'll mark it V7, V5, cost 6, accept, and this is in fact our minimum spanning tree.